Welcome. Last time we saw an intuitive justification of why we can calculate areas of region bounded by two vertical lines, the x-axis and the graph of a function, by integrating the function itself over that interval given by the two vertical lines. Now we are going to look at some examples of this. For now we will limit ourselves to positive functions. We'll worry about what happens in general later on. I'm going to find the area under the graph of y equals e power x, but above the x-axis, and between the two vertical lines x equals 0 and x equals 1. So our formula says the area is the integral from 0 to 1 of the function e power x dx. We take the function, integrate it from the left boundary to the right boundary. After this, it's just a matter of calculating definite integrals. If I can find the antiderivative of the function, and in this case I can, it's just a matter of using the fundamental theorem. So I take an antiderivative of e power x, which would just be e power x, and then take the net change as x goes from 0 to 1. Substitute the upper and lower bounds for the integral and subtract. So this is just e minus 1. So the area of that region is e minus 1. Even though in all the pictures, it looked like I had two vertical lines. The vertical lines might shrink down to a single point, either on one or both sides. So in other words, I can have a region like this, bounded by the x-axis, the line x equals 1, and the graph of y equals x squared. Even though it looks like I have only three sides, I can pretend that there is a vertical line segment of height 0 here. So x goes from 0 to 1, and the region is in between the x-axis and the graph of some non-negative function. In this case also our technique works. You integrate the function, in this case x squared, from the leftmost value of x, which is 0, to the rightmost value of x, which is 1. Again, I will just use the fundamental theorem. The integration is straightforward. And antiderivative for x squared is x cubed over 3. And I take the net change from 0 to 1. So 1 cubed over 3 minus 0 cubed over 3, or 1/3. As I said, it's possible even for both the vertical sides to shrink down to a single point. In other words, you can have a region bounded by the x-axis and the graph of a function which intersects the x-axis at 2 points. So in our example, I have parabola 2 plus x minus x squared, which runs like this, and the x-axis. Together they found this curved region, what's called the parabolic segment. Of course, I can still think of this as area between x-axis and the graph of a function, with x running from the value at this point to the value at this point. Only difference is that now I have to actually find those numbers instead of them being just given to me. You can find these numbers by just drawing the graph on your calculator and tracing it, or you can also do it algebraically. To find these numbers algebraically, basically I have to find the x-intercepts of the parabola, which are solutions of the equation, the function equals 0. Since I have a quadratic, I have to solve a quadratic equation, which I'm going to do by factoring. I'm going to factor out a negative first, so it's a little bit easier to factor. A factorization for x squared minus x minus 2 is x plus 1 times x minus 2. That's 0 if x is negative 1 or 2. So those are the x-intercepts. This point corresponds to x equals negative 1, this point to x equals 2. Region has x running from negative 1 to 2. The area is the integral between those two numbers of the function whose graph gives the top boundary of the region. In other words, it's the integral from negative 1 to 2 of 2 plus x minus x squared dx. Since it's a polynomial, again the integration is straightforward. Just apply the power rule term by term and then take the net change from negative 1 to 2. So plug in negative 1 and plug in 2, take the difference. So I plug in 2 and then you plug in negative 1 and subtract, which gives me this arithmetical expression. And I'll leave it to you to verify that you get 9 over 2. So the area of that region is 9 over 2.